Good afternoon or good morning, everyone, and thank you for joining us for today's webinar on PFAS Visualization Case Studies for Site Characterization, Remediation, and Forensics. My name is Shana Cohen, and I oversee NEWMOA's hazardous waste and waste site cleanup programs. We're excited to have such a great turnout for today's session, which will delve into practical PFAS visualization methods and real-world case studies. Before I cover some logistics, I'd like to quickly introduce NEWMOA, as some of you may not be familiar with the association. The Northeast Waste Management Officials Association, or NEWMOA, is a nonprofit, nonpartisan interstate association that was formed in 1986 by the environmental agency directors of the 6 New England states. By 1990, both New Jersey DEP and New York State DEC had also joined the association. Our role is to foster collaboration across states by sharing information, tools, training, and resources across several program areas, including hazardous waste, solid waste and sustainable materials management, pollution prevention, waste site cleanup, and of course, PFAS. And this is just a picture of the NEWMOA staff along with our board of directors, for those curious. Alrighty, and for a few quick logistics. To minimize background noise, I'm sure you guys have noticed that participant microphones and cameras have been disabled. Please feel free to type questions into the chat as we go, and we'll plan to address those questions at the end of the session. If you'd like to ask a question verbally, please raise your hand and we'll enable your audio and video at that time. Today's webinar is being recorded, and the recording will be posted on the NEWMOA website by the end of the week. However, I will be trimming out the Q&A portion of the session just to give you guys a little bit more freedom to have those discussions. And if anyone experiences any technical issues or has trouble accessing materials on the NEWMOA website, always feel free to reach out and email me. I'm always happy to help. Alrighty. And finally, it is my pleasure to introduce today's speaker, Dr. Grant Carey. Dr. Carey is the president of Porewater Solutions and has more than 30 years of experience specializing in PFAS fate and transport, site characterization and remediation, environmental forensics, groundwater modeling, and related disciplines. He is currently involved in multiple strategic environmental research and development program, SERDEP, and environmental security technology certification program, or ESTCP, projects for the U.S. Department of Defense, with a focus on PFAS remediation. Grant is the co-developer of the Visual PFAS software that will be demonstrated later in today's webinar, and he has also been involved in the development of PFAS e-learning modules, And as if that wasn't enough, Grant also serves as an adjunct research professor at Carleton University and an adjunct professor at the University of Toronto. Also quickly going to note that several members of Dr. Carey's team from Porewater Solutions are joining us on the call today, along with, I believe, Rita Krebs should be here, who is the remedial program manager for Ellsworth Air Force Base. And she's a co-author on one of the case studies featured in today's presentation. And with that, thank you for joining us today, Grant. We're looking forward to your presentation, and I'm going to turn it over to you.
Super, thanks, Shana. Hello, everybody. I'm just going to go window around here, get that minimized. So thanks very much for joining today. I really appreciate you taking the time to come out, and wanted to extend a really special appreciation to Shana and NEWMOA for organizing this webinar. So we have a lot to cover today. I'm not going to go through too quickly, but there's a lot of information here. So happy to answer any questions at the end of this session as well. If you have any questions, or if you want any of the papers we're talking about during the session, feel free to email me, gcarey@porewater.com, and I'll send you that information after the seminar is done. So let me put this in display mode here. So as Shana mentioned, I've been involved in a number of SERDEP and ESTCP projects for U.S. Department of Defense, and most of the work has really been related to remediation of PFAS with in situ absorption barriers. But the one thing we've found over the last few years is that with all the PFAS data we're collecting at these field sites, we've got upgradient wells, in-barrier wells, downgradient wells. We're looking at performance for short chain, long chain PFAS, carboxylate, sulfonate. So we really needed better tools to visualize the data. And that's really kind of spawned what we're talking about today with some of the tools that we've developed and some of the case studies where we're going to demonstrate options that you have for visualizing PFAS at your sites. So one project I'm actually quite proud of, Shana mentioned as well, is this e-learning project we just started this year, or actually 2025, with the STCP. So we're creating 4 PFAS e-learning modules that are going to be freely available to everybody. They'll be online. We'll have online quizzes if anybody needs certificates of completion for their professional licenses. And you can see with the interface, we've got a menu on the left of these modules. So you can come in at any time, go to any special section you like to, or you can just scroll through page by page through these modules from start to finish. We have things like a progress bar at the bottom of the modules, which you can move back and forth on a slide to go back or forward in the audio. You can replay the audio for each slide if you like. So a lot of options here where you can kind of really learn at your own pace. You don't have to listen for an hour and a half right now, like I'm speaking. You could actually have more ability to kind of stop, pause, listen to what you've heard, replay things, etc. So there are 4 modules that we're developing. One has actually been finished now. It's under review by DoD. And we're actually looking for, this is partly for the regulatory community, these modules. So I'd really appreciate if anybody's actually interested in reviewing the modules as they get finished up and giving us your comments. We have an online survey you can do after the module is done. Please send me an email, and we'd love to get your review, comments, any suggestions you have for how we can improve either the modules themselves or even the content. Is there anything here that you think might be missing or that should be added to the different topics we have? We'll make these slides available after the webinar, but basically it's introduction to PFAS, conceptual models, in situ remediation with a couple of different strategies. And I just wanted to point out Dave Adamson and Chuck Newell are instructors for some of these modules. And if you haven't heard them before, they are great speakers. So a lot to look forward to with these. And one other thing I wanted to point out is recently Porewater Solutions has teamed with NSAFE, where we have specialized tools and experts between our different groups. And we found there's a lot of synergy to work on NSAFE projects and Porewater Solutions projects, where we're really kind of focusing more on visualization of PFAS, using specialized modeling tools to evaluate remedies, feasibility studies, and even looking at site-specific soil screening levels with modeling tools and data analysis tools. So that's something that's just been recent, but it's something I'm really looking forward to working with NSAFE on. Okay, so today we've got an hour and a half. I'm going to try and keep this to hour and 10, hour and 15 minutes, so that way there's more time for questions at the end. We're going to go through a really brief PFAS primer, not going to talk a lot about chemistry. It's more about important points, well, in terms of nomenclature, make sure we're talking about the same things. And also talking about, why we group things the way we do when we're visualizing data. We'll go through an overview of different visualization methods and when we might want to apply them and why we apply them. And then we'll start with a pretty detailed case study at Ellsworth Air Force Base, where we're looking at AFFF impacted conditions in different source zones. And we're talking about how these methods can be used for site characterization or remediation analysis or forensics, really at any site. Then we're going to go through another section 4. I've just finished publishing 2 more papers with Rita Krebs and a group of others on looking at the VADO zone and data at Ellsworth Air Force Base. We're looking at pore water sample data. We're looking at SPLP and how those compare to pore water results. Some really cool findings with that. And we used visualization for a lot of that. So that's going to be part of this webinar as well. And we'll wrap up with a few more case studies depending on time and question and answer at the end. Okay, so I'm going to assume a lot of you are pretty familiar with PFAS. I'm just really talking about classes or abbreviations so we're consistent here. So everybody probably knows perfluoroalkyl acids or PFAS. That's where most of the regulated PFAS compounds come from, that class. And we typically break that up into 2 groups. There's the sulfonates bucket and the carboxylates bucket, like PFOS and PFOA. And then with method 1633, we've got 40 analytes in total. We've got a number of PFAS. We've also got a number of precursors. And what we're doing is we're breaking those precursors up into 2 different types, depending on how PFAS were manufactured. There's precursors that were generated from electrochemical fluorination, which is a manufacturing process. And there's a different set of precursors, also analytes in method 1633, which come from manufacturing with the fluorotelomerization method. And then there's a final class with the 40 analytes in method 1633, the perfluoroether acids. These are really the replacement PFAS, HFPODA, which is a Gen X class, is part of that as well. So these are all the different analytes, the PFAS. You can see the sulfonates on the left above the red bucket, carboxylates above the blue bucket. Then we've got our precursors, the ECF-based precursors. All might actually degrade to PFAS under natural conditions, typically aerobic. And then we've got a series of fluorotelomere-based precursors that degrade to a range of C4 to C8 carboxylates. And then we've got the PFAS on the right side. These are all the analytes, the 40 analytes in method 1633. And then in terms of AFFF impacted sites, a lot of the work I do is at AFFF impacted sites. We tend to see high concentrations of at least one of 6,2 FTS or 8,2 FTS. These are from fluorotelomere-based AFFF products. And you can see their transformation products, when they do biodegrade, is typically under aerobic conditions. And they biodegrade each one to 3 different daughter products. So 6,2 FTS will biodegrade mainly to PFHXA, a little bit lesser to PFPEA, and then a fair bit less to PFBA. But all 3 of those are daughter products. And A2FTS, when that's biodegrading aerobically under natural conditions, PFOA is produced. And that's certainly probably the most regulated compound, PFOA and PFAS, at the state and federal level. So we really need to be aware of what are the precursor concentrations that may degrade to regulated compounds, and do we see evidence of biotransformation? And there are some visualization strategies we can use to actually look for that kind of evidence. And I'll go through an example with the case studies coming up. And you'll see on the left, below 6,2 FTS, I have modern AFFF. And below A2 FTS, I have legacy AFFF. So the original AFFF products produced through fluorotelomerization were mainly longer chain precursors that resulted in a fair bit of A2 FTS and PFOA in subsurface impacts. And the modern AFFF, that's more C6 precursors, resulting in 6,2 FTS and the shorter chain carboxylates. So if we see a lot of short chain carboxylates and not much in the way of PFOA at an AFFF impacted site, we know that was probably more modern AFFF that was used in that area. And that starts to tell us timing of when things were released. We can actually, that's why we might want to separate and look for, do we see evidence of modern or legacy AFFF products used in a certain source area? We can get at when it might have actually been used or released. One thing to keep in mind, though, and I'm sure a lot of you are aware of this, is that because these precursors do biodegrade naturally, sometimes to regulated PFAS, we want to make sure if we're incorporating a remedy at a site, maybe enhanced bioremediation for hydrocarbons or chemical oxidation, those types of remedies can change redox conditions. And if they make things more oxidizing, for example, that could stimulate the biodegradation of these precursors to their PFAA daughter products. So we really need to be careful of that if you're looking at remediating non-PFAS at a site. I've seen some sites where PFOA, for example, increased by a factor of 10 where chemical oxidation would be done. So just something to be aware of. So with PFAS, I'm sure everybody's aware, the simple molecule structure, there's a tail and then there's a head. We've got sulfonate heads and we've got carboxylate heads. And you can see that the tail actually has varying length depending on the compound. The gray atoms in these tails, those are the carbon atoms, and the green atoms are the fluorine atoms. So the longer the tail, the more hydrophobic the compound's going to be. The more hydrophobic it is, the more it's going to absorb to natural organic matter or carbon in soil, the more it might absorb to air-water interfaces in the vadose zone, or Napa water interfaces, or sorbents like granular activated carbon or colloidal activated carbon. So it sometimes helps if you're looking at remediation, or let's say you're doing an RI, you might want to make sure you're looking at, well, how much do we have in the way of long chains versus short chains? And where is that mass being retained relative to their absorption capacity? So as I mentioned, so the absorption can affect how much PFAS are retained in the vadose zone, how much might be retained below the water table, say if there's Napa below the water table. It does affect PFAS travel time in expanding plumes, where absorption does affect retardation coefficients. It also affects viability of remediation. If you have regulated short chains, you want to make sure you characterize what their concentrations are, how they vary across the site, because short chains are harder to remediate using absorption-based technologies, and it can affect remediation time frame. So if you're putting, say, a pump and treat system to do hydraulic containment or an absorption barrier for chemical containment, the mass that's down gradient that's left after you install that remedy, the PFAS have to desorb from carbon in the soil and eventually get flushed out. And the time of that flushing depends on how much is actually absorbed to carbon in the soil when the remedy is installed in that down gradient area. So that's just something to be aware of. So there's a great ITRC has done an amazing job, I have to say. I was involved with the PFAS guidance manual up until about 2020, but it's really evolved since then. Lots of great information there. One thing I find really helpful is the ITRC AFFF fact sheet from 2024, available online. They go through a really good discussion of legacy ECF. This is AFFF products produced using electrochemical fluorination up until 2002. And only one company produced the ECF-based products. 3M produced using that manufacturing process. All the other AFFF manufacturers use fluorotelomerization. But the thing is, we can actually start to tell which products may have been used in source areas, or at least predominantly used, based on the impacts we measure in soil and groundwater. So ECF-based AFFF products tend to result in higher PFAS and PFHXS in soil and groundwater, where releases may have occurred, and lower concentrations of carboxylates like PFOA. And then if we look at the fluorotelmer products, I mentioned before about the legacy fluorotelmers, longer chain precursors tend to see higher PFOA in groundwater, more A2FTS. The modern FT products, I've seen documentation that modern FT products were used at least back to 2005. And those impacts tend to be shorter chain carboxylates in soil and groundwater and 6,2-FTS. So depending on what you see in soil and groundwater, you might see that maybe one of these products was predominantly used in an area, or maybe a mix. But that tells us what kind of clues we can look for with visualization. We can look at what's the relative sulfonate versus carboxylate concentrations, what are the ratios of long chain versus short chain carboxylates, which tell us, was it more of a legacy or modern FT product used in that certain area? Okay, so let's go through visualization methods. So 40 PFAS analytes, precursors, regulated PFAs, perfluoroether acids. We've got co-occurring chemicals we want to make sure we characterize if we're looking at remediation in case that affects PFAS remediation. We've got redox indicators because we want to know our precursors biodegrading to regulated PFAS. So that results in a lot of chemicals for each soil and groundwater sample we collect, results in big tables like this. The old way, and by old I mean like 2 years ago, way of plotting these data might have been these, I call them table plots. You have small tables at each location. You summarize the regulated compound concentrations for certain events, but it's not really a visualization. You're really tabulating the data and putting it on a map, but I can't look at that map and tell you right away where concentrations are highest and where they're lowest. That's where visualization can help to add that extra layer of information. So it really raises the question, with all these compounds we have to characterize, how can we effectively analyze and then communicate all these data to project stakeholders? So the simple ways are, first of all, focus on single species. It could be total PFAS. Maybe you've only got 2 regulated compounds, PFAS and PFOA at a site. You can do 2 maps, and you can show PFAS concentrations on one, PFOA on another. Typically, if you have a lot of wells, you can use symbols and just plot different colors for different concentration intervals. One thing that I find really effective is actually what I call exceedance magnitudes. I think Chuck Newell framed that term actually. And it's really just the ratio of a PFAS, let's say PFAS or PFOA concentration at a well. It's a ratio of that to the cleanup criterion. So if you have an exceedance magnitude of 10, it means that the well concentration is 10 times the cleanup criterion. That's all it is. So any exceedance magnitude is greater than 1, exceedances that might have to be dealt with. If it's less than one, you don't have an exceedance there. So very simple, helps you to see where exceedances occur at a site and evaluate how many orders of magnitude reduction do you need to achieve to meet remedial goals. And then there's also concentration contours, an obvious way we can evaluate data for one species at a time, but you need a fair bit of well data to actually be able to do that. So one thing that we've been doing more of in the last few years is really looking at what I call PFAS interrelationships. How do some group concentrations compare to other groups? There's many reasons why we look at that. One is maybe we want one map that shows all the regulated PFAS of concern and where the exceedances occur. So multiple chemicals on a map. Sometimes we look at short versus long chain. If we want to know, will an absorption remedy work? We might need to look at both types of those, sulfonates versus carboxylates. But number 2 and 3 tell us what kind of AFFF products might have been used. They're used quite a bit in source forensics. Which sources are contributing predominantly to a commingled plume, for example. Precursor degradation, we need to look at the parent products, the precursors, and the daughter products on the same map. And we want to see how those ratios are changing along a flow path, for example. We might want to see, well, how are PFAS attenuating along a flow path? Some PFAS might attenuate at different rates. Or we might want to look at site versus background concentrations for a number of PFAS species on a single map. Remediation monitoring and source fingerprinting, other reasons why we need to often look at more than one species on a map. So a couple ways you can do that. One is if you have a single sample where you want to look at this and you want to look at all the analytes, all 40 analytes from method 1633. Jeff Gamlin came up with a paper with a really cool visualization approach using 3D bars, and that shows the results for all of these 40 analytes. And then there's the heat matrix on the right. Same concept, just with a simpler visualization form. I'll show you an example of that in a minute. And we've actually got a PowerPoint template where you can do this manually on your own for any site. We tend to do this more for source areas. So we'll take the maximum PFAS concentrations from method 1633 for each source area. And each source area has its own heat matrix. And we'll basically put them side by side and see. That helps to visualize not only where the highest concentrations are, but what's the relative ratio of precursors to PFAS in different source areas. Maybe some have had more biodegradation than others. And then a more sophisticated way, but one that helps really with looking at spatial trends and is radial diagram maps or stack bar maps or pie diagram maps. The radial diagrams are more for looking at magnitudes of multiple species on the same map and how they change with distance downgradient from a source area or maybe between source areas, whereas stack bar maps and pie diagram maps are more for looking at proportions and how those change. Those are great for forensic tools as well. And the mapping, we can also look at temporal trends over time. So by putting them on a map, now we're adding a spatial dimension to it, which can actually add a lot more valuable information. And we'll look at some examples of this with our different case studies. So this is the heat matrix. So what we did as part of our the first e-learning module, the introduction to PFAS, we prepared this. It's available for download with that module, and I'm happy to send this to anybody if you want to send me an email. It's just a PowerPoint template, and you can set this up so you just have a table of concentrations next to you. You can see on the x-axis, we basically have the number of carbon atoms. So the shortest tails, the shortest molecules, are at the left, PFBS, PFBA. And if you go from left to right, you see the carbon numbers increase and the molecules get longer. And then on the y-axis, we've really got rows for the different classes of compounds. We've got sulfonates and carboxylates, and then we've got the precursors above and below that degrade to sulfonates and carboxylates. And we've got a couple rows at the bottom for PFAS. So just to show you how it works, with a PowerPoint template, or you can create your own software to do this. You can add colors for different ranges of concentration intervals. So the dark red here, this is a hypothetical site. Dark red are highest concentrations above 100 microgram per liter. You can see we've got high PFAS, high PFHXS, so obviously a lot of ECF-based AFFF was used in the source area. We've also got pretty high 6,2 FTS and high daughter products, so obviously a lot of degradation of that 6,2-FTS precursor has happened, we've got pretty low concentrations of 8,2-FTS and low concentrations of PFOA and PFHPA. So if you think about it, what are the two AFFF products used most predominantly at that site? So one thing I do with this is sometimes we'll actually add these tables, summary tables for each source area. You can look at the totals. You can see the sulfonates and ECF precursors, about 1,500 microgram per liter total. Carboxylates and the FT-based precursors, around the same. And the precursors are mainly, and the daughter products are all indicative of that modern FT-based AFFF. We know ECF-based AFFF was the first one used by military installations, and the FT-based came in after. So maybe at this site, they were using more of the ECF-based until it stopped being manufactured, or around that time, whenever that was. It looks like early to mid-2000s, maybe they switched to the legacy FT-based. But there's not a lot of modern, they switched to the modern FT-based with the shorter chain 6,2-FTS. So that's the kind of thing you can start to see which products might have been more predominantly used in source areas and when transitions may have occurred, just roughly. We won't know an exact year for that. So the value of doing radial diagrams and stack bars, that's the reason why we developed this Visual PFAS software. We are making, it was available commercially earlier this year. We found that most of the large consulting firms are actually developing their own PFAS visualization tools. None that I've seen yet with radial diagrams or stack bar maps, but I'm sure they're coming. So we're no longer selling it commercially, but if there are regulatory agencies that are interested, we're happy to provide you with free licenses. We can give you some basic support with that as well. So if you'd like to get some help kind of getting up to speed, let us know, send me an email, and we can do a hands-on demo or send you some demo videos so you see how it works if you think it might be something of use to your agency. I've also been involved with NGWA. They have a committee on developing a white paper on PFAS forensic methods. And a lot of these are really more statistical. And today I'm going to focus really more on the visualization. But there's even more than what I've mentioned here in terms of what we can do for forensic evaluations. So I'm going to go through now a characterization for Ellsworth Air Force Base, where we actually published a paper recently. Feel free to email me if you want a copy, where we looked at the AFFF source areas at the site, and also at the former fire training area where we looked at conditions in more detail in terms of mapping. So Rita Krebs was a co-author I'd really like to acknowledge. Rita's the remedial program manager at Ellsworth Air Force Base. And I have to say, the data sets collected at Ellsworth Air Force Base are fantastic. Tons of data for us to use. And we've really been experimenting about what visualization methods work, what doesn't work, what's not needed. And Rita's been great with providing us support with history of the site, the data. And I have to say, it's very rare as a consultant to be able to develop visualization methods and then publish them and show the data from the site. So I really appreciate the access to the data that we've had with Rita. We've also had Jeremiah Duncan from GZA was a co-author on the paper. And then you can see a number of folks from Porewater Solutions, Gabe Carey, Mia, Jillian, and Kira as well. So at this site, we have 14 known AFFF source areas. So I'm actually going to show visualization results from the site inspection, which was done back in 2018 or so. More recently, they've done a detailed RI, but I'm just going to focus for now on the site inspection results, just as a way to demonstrate the visualization options we have. And you can see AFFF1, that's the current fire training area combined with the former fire training area as well. That's in the south part of the map that we're seeing here. And you can see there's a number of other AFFF source areas, some from crash responses, some from storage and use of AFFF in different parts of the site. So the most simple radial diagram, I'm going to show you the layers that we add so you can see the rationale for why we end up with what we have for a PFAS radial diagram. So simplest form, 4 axes, 4 PFAS chemicals. This is a radial diagram showing concentrations for one well, GW4, downgrading of a source area at the site. And we're showing, you can see data from a monitoring event in 2011, the first event where PFAS data were actually measured in groundwater. Now we're on the left, we have the precursor, FHXSA, which biodegrades under some conditions aerobically to PFHXS, which is on the right axis. And we're also showing PFBS on the top and PFAS on the bottom. So one thing I do with radial diagrams is I almost always add a second data series. I find I actually tend to look more at the gaps between the series rather than trying to look at one series from zero. So the reference series, those are concentrations that are going to be consistent for every well we show on a radial diagram map. They all have the same reference series concentrations. And in this case, I'm showing the maximum site inspection concentrations base-wide as the reference series. Actually, this is the source area. This is the former fire training area, I think. So they're the same for all wells, and then the blue series are the well-specific concentrations. Now this is log scale, which makes, and AFFF sites, you tend to have a wide range of concentrations, orders of magnitude, so you need log scale. Smaller concentration sites, arithmetic scale is fine. The advantage of log scale is I can actually use the tick marks. So let's look at PFAS. The purple data series is the source area, a couple 100 feet upgraded into this monitoring well. And we see we've got, when you count each pair of tick marks represents a 1 order of magnitude change in concentration between the data series. So there's 2 pairs of tick marks between these 2 data series, or 1.5. So I know that we have 1.5 orders of magnitude difference between the upgradient source area and what's at the well in the blue. And I know we have a smaller gap, smaller difference, about a 1/2 order of magnitude for PFHXS and PFBS, and about a 1 order of magnitude change for FHXSA. So radial diagrams, at least at AFFF sites, are more about counting the tick marks and measuring how many orders of magnitude change do you have between source areas or along a flow path. And one other layer of information we add, which I find really helpful, whether you're, for example, we add exceedance symbols. So for any PFAS of concern on a radial diagram, we have the option of plotting exceedances where they occur. Those are the red symbols here. And we can show non-detect symbols. So if you're doing remediation and you're looking down gradient, you really want to see a lot of non-detect symbols. So whether it's detected or non-detected can help with your remediation analysis. So this is a layer of very simple information, but can actually be quite informative with no extra cost. So that's why we put our symbols on the figures. Now at this site, there was a really good paper by McGuire et al. 2014. They actually had implemented a hydrocarbon remedy involving dissolved oxygen infusion wells to get high concentrations of oxygen into groundwater to remediate hydrocarbons downgradient of the source area. This is something they set up before they even knew that PFAS were at this site. And with obviously oxygen injection, that can stimulate precursor degradation. So looking at the downgradient well, we see the precursor, FHXSA, has declined substantially by orders of magnitude at the well that's just downgrading or next to this dissolved oxygen infusion well. And it's the green symbol shows it's non-detect. So that tells us that at least near that DO infusion well, the precursor degraded. We also see that each of these species increased compared to the upgradient well. So that's showing we've got precursor biodegradation and daughter product increases in concentration. Same thing we used to do with chlorinated solvents. Now we can do with PFAS to look for evidence of biotransformations. So now we're going to switch to look at the base-wide map, and we're going to look at a radial diagram to characterize the different AFFF source areas. And with these, what I do is I plot sulfonates on the top axes, and I plot carboxylates on the bottom axes. And then you'll see I've got long chain on the left side, going from left to right to the short chain for both sulfonates and carboxylates. So the left side is long chain, the right side is short chain. So now we're grouping these radial diagrams so we can look at quickly to see differences in concentration for sulfonates versus carboxylates, short chain versus long chain. So that's one thing we do with a lot of our graphics is group things that way to look for those kind of trends. So now if we look at the map, AFFF1, we see that the source area concentrations at AFFF1 are the same as the reference series. And that's because that's where the concentrations are highest at the site. And remember that table map I showed before, you couldn't really tell where things were high or low. Well, we can in seconds see, okay, the highest concentrations right here, lowest concentrations, a lot of non-detect symbols down here where there was a former crash, obviously no impact here. AFFF 12, we're going to look at this in a few minutes with some stack bars, but you can see the long chain carboxylates, PFNA is this axis, PFOA is here. Those are pretty low concentration compared to the short chain carboxylates that are orders of magnitude more. So that's telling us, okay, we've got a lot more short chain carboxylates. And now if you remember, that kind of tells us what AFFF product was used. Shorter chains, so the more modern FT-based product probably had a lot more use in this area than the legacy FT-based product. So stack bars are more for forensics, but they really help tell us, okay, what was the relative, in this case, we're looking at the orange zone represents total sulfonates. The blue zone represents total carboxylates. They total up to the total PFAS in groundwater and the source area. 100% just means every location has 100% here. So this just tells us at this one location where we're looking at the legend, 70% of PFAS are made up of sulfonates and 30% are made up of carboxylates. So that's starting to tell us, well, maybe the ECF-based AFFFs were more predominantly used. You have to do a lot more work to do a true mass balance. You have to look at what's in the vadose zone, what's below the water table, but it starts to tell us some clues about what might have been used and maybe more recently, not as much used as maybe in the past. So just looking at this on a map, we can see AFFF1, the current and former fire training area. A little over 60% of that is sulfonates, which mainly come from the ECF-based AFFF. And we see the difference here. It's actually only 40% sulfonates at AFFF 12. So it looks like more of the FT-based product was used, but certainly they did have ECF-based AFFF products used in that area as well. And then you look at different again, AFFF3, now we've got 85% sulfonates. AFFF 6 is the opposite, only about 20% sulfonates. So you start to see different products being used or handled in different areas. And that's not surprising. That's something we see at a lot of these sites. Some sites are more of a mixture of different products. Some sites might have more predominant use of one versus the other. And then remember, we wanted to look at long versus short chain to tell us the short chain carboxylates come more from the modern FT AFFF, which were used only starting in the mid to late 2000s, or were they coming from the long chain carboxylates? So you'll see one thing with this is for short, I really want to know short chain. So I tend to group all the short chains with one color and different shades of green in this case. The lightest green for the shortest chain, darkest green for the longest chain, PFHXA, which is still a short chain carboxylate. And then the yellows, oranges, and reds for the longer chain. And now when we map those, we can see looking back at AFFF 12, remember the radial diagram that showed higher concentrations of the short chain carboxylates than PFOA and PFNA? And this is showing, yeah, it's 95% of carboxylates at AFFF 12 are short chain. And that tells us for sure the FT-based AFFF was predominantly used, and maybe the legacy FT-based product wasn't used in that area. Hard to say it was never used, but certainly we know what was predominantly used. We also know there was a storage tank that stored AFFF in that area during the 1980s. It was abandoned in around 1990. And we know because the modern FT-based products weren't used until early to mid 2000s, they couldn't have been stored in that tank. So that's starting to tell us, okay, we can eliminate that as a source for these modern FT-based products. We're starting to look at timing of when some products might have been released. So starting to get more information. And if you're thinking about different sites with different sources like this, and if we're looking at a plume down gradient, sometimes it's really clear one source has a fingerprint that looks a lot like a plume, whereas the other source isn't as implicated. So that's where this kind of thing can come in handy. And I just wanted to mention, like, stack bars are actually pretty much the same concept as pie diagrams. We're just looking at proportions. We're not looking at magnitudes. You will notice, though, on stack bar and pie diagram maps, I actually do show, in this case, the total carboxylates. I add them in brackets because magnitudes sometimes are helpful. So the stack bars show proportion, and I add the numbers in brackets next to each stack bar to get an indication of magnitude. If it's a really low magnitude, like AFFF 7, 0.05 is the total, I'm not really going to put a lot of weight on that fingerprint. But something like AFFF 1, obviously a higher concentration, that's when the fingerprint has more meaning. So that's why I like to put the magnitudes on for these proportional type visualization approaches. And one thing with stack bars, you'll see we put the tick marks on the left of each stack bar on the map. And that makes it much easier. So I can look at this dark green and I can tell you, well, that's slightly over 20%, maybe 22, 23% of carboxylates at AFFF 5. And that's where the tick marks are really helpful. I can more precisely tell you the proportion of each chemical in the stack bar. Whereas if I came over here and look at the dark green, I'm not going to, I just intuitively can't tell you what that magnitude is going to be. I can tell you it's between 25 and maybe 20 and 50%, but the stack bars for me are a little bit easier to scale what the proportions are for each chemical. That's why I like to use those. And one other thing that we found really useful at Ellsworth Air Force Base was plotting top data. So if you remember how these work, these top assays, they collect a groundwater sample, and that groundwater sample is going to have some precursors. It's going to have PFAS, carboxylates, maybe sulfonates. When they do the top assay, it's an aggressive chemical oxidation that will oxidize, I don't know if it's all precursors, but it's a lot of the precursors. And through the oxidation process, they only go to carboxylates. So it just tells us, do we have precursors that are shorter chain or longer chain, degrading to short chain, in this case, carboxylates or long chain carboxylates. And here I find radial diagrams quite helpful. This is a legend showing the gray series is the sample, the groundwater sample before the top assay. Those are just the carboxylates measured in groundwater before any chemical oxidation was done. And the red data series tells us what carboxylates were measured after the oxidation had been finished. And you can see for PFHXA, that's a C6 compound, short chain, that close to doubled after the top assay. So that tells us that clearly there were some precursors in that sample that were shorter chain that do biodegrade to a C6. And same thing with the others, PFPEA, PFBA, they all about doubled after the oxidation, but the long chain carboxylates didn't change. So that tells us in this sample, there really weren't longer chain precursors that would degrade to a C7 or C8 compound, but there certainly were that degrade to the short chains. And then you put them on a map. This is where we know that, excuse me, precursors do tend to filter out. They tend to absorb pretty strongly in source areas. They don't move as much down gradient. And we can see pretty consistently, sorry, let me turn that off. Pretty consistently, the long chains don't have change or much of change after the top assays, whereas a lot of the short chains do. And that's so here, this location, not much in the way of C6 increase, but there were C4 and C5 increases. Pretty much no C7 or C8 either. So we can start to see what the precursor composition might look like, even if there are precursors in the sample that we didn't measure with method 1633. So just another way of visualizing data and mapping it spatially to start looking at how many precursors might move down gradient from the source area. So I'm going to go through this fairly quickly, but I will tell you with this paper, one thing we wondered, can we come up with a visualization approach that lets us actually show the effects of biotransformation besides looking at a reduction in the precursor concentration and an increase in the daughter product? That's harder to show on a flow path. We were wondering, can we use ratios to look at this? So we looked at the ratio of the parent concentration, 6,2 FTS in this case, over one of the daughter product concentrations, let's say PFHXA. And if you look on the right, when biodegradation is occurring, that precursor, that's the parent species, that's biodegrading. So its concentration goes down. The daughter product, like PFHXA, it's going up because it's a daughter product. It's getting produced. So the ratio will go down when biodegradation is occurring. So in a source area, you might see a higher ratio. If biodegradation is occurring along a flow path where you've got aerobic conditions, then you're going to see that ratio decrease with distance from the source area. And this shows a radial diagram. We've got each of the axes represents a ratio between the parent and one of the daughter products. And you can see this is a well that's near a dissolved oxygen diffusion well. And we can see in the source area, generally the ratio is about 1. Precursors were, the 6,2-FTS was similar in concentration to the daughter products. And you can see down gradient near an oxygen diffusion well, we had about a 1.5 orders of magnitude decrease in that ratio for PFHXA, which is the main daughter product. And then PFPEA reduced by about an order of magnitude in the ratio, and PFBA by about half an order of magnitude. And that's the kind of scale you'd expect when biodegradation is occurring. We also have to check, is the plume stable in time? If it's not stable, this might be the effect of differential adsorption. But if your plume is stable, which it is in a lot of source areas where things have been happening for decades, then this tells us, yeah, we've probably had biodegradation. And the location next to a dissolved oxygen well makes that more clear as well. And then we can just map that. And we can see generally not a lot of biodegradation occurring, except the plus signs of the dissolved oxygen diffusion wells. This is where we clearly had a fair bit of biodegradation occurring. Okay, so that's looking at AFFF source areas. Now we're going to go to the VADO zone and look at Ellsworth Air Force Base again. We recently just published 2 papers where we used a combination of methods, number of visualization approaches. We also did some cross sections, which you see on the right, and some mass balance equations for a couple of reasons. What we wanted to do, this site at Ellsworth Air Force Base, they've had 2 different sets of lysimeters installed and samples collected for pore water. And they've got co-located samples for soil at each lysimeter. The second set of lysimeters installed for the RI also had co-located SPLP results. So they took soil samples, did SPLP tests at each RI lysimeter, and we can directly compare the SPLP leachate concentrations to pore water for all these different PFAS constituents, short chain and long chain, to see how they compare. And the results are really interesting. So I'm going to walk through that. The reason being that SPLP, certainly it can be used to evaluate KD, like how much absorption occurs when you've got saturated samples. It's a little bit harder to be representative of pore water because of some processes occurring that SPLP doesn't measure. And I'll talk about those as I show the results. So again, I want to acknowledge my co-authors, Rita Krebs, again, with amazing data sets here. Dave Adamson from GSI, Kevin Mumford from Queen's University, Bo Guo from University of Arizona. Number of staff from Porewater Solutions, Mia, Gabe, Kira, Sabrina, and Maya. Everybody was super helpful with these papers, getting all the data analyzed and presented. So I find photographs are, if you're doing visualization, photographs always help. Let's show what reality looks like. Photograph on the right was from Rita. This is the former burn pit that we see in the middle of this area. This is operating unit 1, which is the former fire training area, bounded by the red line here. And you can see if you look on the map on the right, the orange area is that former burn pit area. OU1 is the area designated here. And you can see the current fire training area up on the top, where obviously a lot more concrete. This is the line fire training area. They actually stopped using the former fire training area in 1990 and switched over to this line current fire training area. The Air Force did this across the board. So it's interesting because now we've got the former fire training area where no releases of AFFF occurred since 1990 for the last 35 years. So that helps us with our data assessment as well. So VADO zone, just some really simple reminders here. We've got the unsaturated zone where you've got water and air in the pore spaces. And we've got the capillary fringe just above the water table, which is 100% saturated, very little air, maybe some air bubbles. But the whole thing combined, the capillary fringe plus the unsaturated zone is the vadose zone. Normally, unsaturated zone and vadose zone are kind of used interchangeably. There's a slight difference in their definition, though. So the key thing about the vadose zone with PFAS, which are unique from a lot of the chemicals I'm personally used to working with, is that in the vadose zone, let's look at, say, a higher part of a vadose zone where you've got less water present. Water is always wetting around the soil grains. And we've got air pockets in between these water rings. So we've got basically long air-water interfaces where there's low water saturation. The more these pore spaces fill up with water, the smaller the area is going to be where you have air-water interfaces. And remember before we talked about how PFAS absorb because they have surfactant properties, especially the longer chain PFAS like PFAS, 6,2-FTS, PFHXS, they absorb really well to the air-water interface. That's just how these surfactants work. So that's another compartment where we can find a lot of mass in the vadose zone. So if you're looking at when we take a soil sample and it's measured in the lab, we're actually measuring PFAS mass across 3 compartments. We're measuring PFAS mass that before the sample was taken was in the pore water or in the aqueous phase. We're measuring mass that was absorbed to natural organic matter coating the soil particles, and we're measuring mass that was absorbed to the air-water interface. Now for PFOS, when you have low water saturation, like in the top part of a vadose zone, a lot of that PFAS is at that air-water interface, and a lot less will be absorbed to natural organic matter or in the pore water phase. The shorter chain compounds like PFBA, they really don't absorb well to the air-water interface. You're going to find a lot more of their mass, more in the pore water, a little bit absorbed to the natural organic matter. And Mark Brousseau from University of Arizona came out with a classic paper in 2018, and it really talked about how these PFAS, because they're surfactants, will absorb to that air-water interface. And in the chart on the right, the orange line shows what the retardation factor looks like, mainly from just absorption to carbon in soil. And the blue line represents the increased retardation, which Mark calculated in 2018, from absorption at the air-water interface for PFAS. This is before a lot of field work's been done. I think we understand it better, know the coefficients of absorption better, but he showed clearly you can get a lot of absorption at that air-water interface. So when we calculate the retardation factor below the water table, pretty simple. It's really just involving KD is that linear isotherm, the product of KOC and fraction of organic carbon, FOC. But above the water table, now we've got an extra term. Now we have the absorption coefficient for PFAS. We have the area of the air-water interface divided by the water porosity. So that's an extra term that for some PFAS can be quite significant. And this comes into play when we ask the question, can we use SPLP leachate concentrations to approximate pore water concentrations? And we'll show you how that played out with data from Ellsworth. So Hunter Anderson published a paper in 2022, did a lot of work with wood. They did a great job putting in lysimeters, and you can see they were putting lysimeters in to estimate mass discharge in the former fire training area around that former burn pit location. And then the other lysimeters installed during the RI, some in the same area, 3 here, and the rest kind of installed farther out. And this is the current fire training area up here. So one thing we did in the first paper, and if anybody wants copies of these, the first paper is probably a week or 2 from being published online at the Remediation Journal. Second paper is being submitted this Friday, but I'm happy to send a draft of that to anybody who's interested. So the first paper is looking at pore water sample reproducibility and representativeness. We wanted to make sure, using multiple lines of evidence, can we use the pore water data to evaluate mass discharge? So one thing we did with radial diagrams, because we've got so much data, we've got 4 monitoring events, we've got a number of lysimeters, 12 lysimeters installed in Hunter Anderson's study. And by using radial diagrams, we plotted one data series for each monitoring event. And we can see the first event, Q1, that's the light blue shaded area. that's smaller in concentration by about half to 1 order of magnitude compared to all the other events. The other events are a lot closer in concentration. And that's kind of typical for some sites where when you install the lysimeters, you're injecting water during the drilling process. It could be that the first set of samples from the event conducted just a couple weeks after lysimeter installation may have been affected by dilution from that injected water during drilling. But we can see quarters 2, 3, and 4 are all pretty similar. And when we plot them on the map, we can see same thing with all these lysimeters. Quarters 2, 3, and 4 are all pretty similar. Quarter 1, though, for the most part, is less. Not so much for PFAS, but certainly for the other compounds. PFAS is this axis up here to the top left. So we can see, okay, maybe that first event's not representative, but quarters 2, 3, and 4 are. We did a fair bit of work looking in the paper at sample yields. Is there a threshold cutoff where if you below it, you don't have enough sample yield to get a representative pore water sample? We found representative results as long as the sample yield was 10 milliliters or more. 5 or less, well, 5 milliliters wasn't enough. That clearly had unrepresentative results. But everything above 10 or higher seemed to work pretty well. And then we looked at the RI lysimeters, same process. Now we only have 2 monitoring events for the RI lysimeters, November 2021, which is the red line or orange line, and April 2022, which is the blue line. And you can see in this legend for the one lysimeter we're showing here, PFAS and 6,2-FTS are higher than the second event. All the other PFAS are lower in the first event. So the first event has higher long chain species that absorb really well to the air-water interface, but everything else is lower. So it could be that this also was affected by dilution from lysimeter installation, and maybe the long chains had higher concentrations because the water saturation was higher in November 2021 than April 2022, and that would result in higher pore water concentrations for the long chains. So anyway, to make a long story short, we only use the second event as being the representative one here. And same thing, you can look when you plot this on a map. The nice thing about radar diagrams, you can show all the locations on a single map. Same thing basically for all these locations. Generally higher for PFAS and 6,2-FTS, not all the time, but a lot of the time. So then what we did, we actually created one combined radar diagram map that actually shows 2 sets of radar diagrams. There's the shallow, there's nested lysimeters installed in the 2022 study that Hunter Anderson did with wood. And you can see the shallow lysimeters tend to be much higher in concentration. That's this orange data series, than the deep lysimeters shown over top. And in this example in the legend, the shallow concentrations are orders of magnitude higher. And you can see that's definitely like lysimeter 107. You can see that's the one from the legend. The long chains are orders of magnitude higher. The differences get smaller as you go from left to right, as you go from long chain to short chain. So for the compounds that don't absorb as well to the air-water interface, you have less of a difference between shallow and deep pore water concentrations at this location. And that's telling us, okay, well, the mechanism probably resulting in attenuation between shallow and deep is related at least partially to the absorption of long chains to the air-water interface. You don't see that with these other lysimeters. You see pretty similar differences between the 2 data series, shallow and deep, for all the PFAS at 104 and at 106. So there, we are seeing some places where it might be more physical restraints in terms of flow. There's limited flow recharge at this site because of high evapotranspiration, low precipitation at the site. So there's some places where we're just not getting a lot of downward vertical flow, and that might be more the reason why we see attenuation at 104 and 106. But clearly, partitioning to the air-water interface is having more an effect at 107. So that's one of the advantages of plotting shallow and deep data on a single map. And then one thing we did too, because there was a question raised, Costanza et al. Had a really good paper from last year, 2025. They talked a little bit about this site and pore water sampling in general. And one of the questions they raised was about this site was they said because of the attenuation observed in pore water between shallow and deep, it seemed to raise a question about the reliability of the data. So one thing we did is we looked at soil concentrations for PFAS. So this is the ground surface just above elevation 3,190 feet. And we're going down about 15 to 20 feet. Water table's at about 18 feet here. And you can see at the right at just below the ground surface, total soil concentration is 100,000 microgram per kilogram for the sum of 7 PFAS of interest. And down at 15 feet, the concentration has dropped to 52. And releases haven't occurred in this area since 1990. So this is about 30 years where releases haven't occurred. So you can clearly see a lot of masses being retained up here in the top couple feet. And then we've got higher concentrations here, and they do drop down quite a bit. And we see the water saturations on the left. So we go through all this in our paper, basically to justify why we do see that pore water attenuation we observed. It's consistent with the soil attenuation that we observed as well. So that's one thing that's helpful. If you're doing vadosome characterization, collecting multiple soil samples with depth can really help to verify pore water samples or other types of samples you're collecting. Okay, so the next part of the second paper was really looking at SPLP. This can be used to estimate the KD parameter for PFAS under saturated conditions. Sometimes it might be used to look at to try and use it as a proxy where pore water samples might not be available. But there's a concern. Well, what we found is SPLP leachate concentrations really did not match pore water concentrations. And there's two mechanisms why that is. The first is dilution. So the way the SPLP tests work, we take a soil sample, usually we take a sample from the field, the lab will measure out 0.1 kilograms, and that works out to be normal soil porosity, bulk density. That's in the field, in situ, that's a volume of about 0.06 liters. And that soil is then mixed with 2 liters of water in the SPLP test. It's a 20 times mass ratio, liquid to solid. So a lot of people think, well, the dilution factor is 20 times between SPLP and what's measured in situ and pore water. But that's a mass ratio. That's not the volume ratio. So if you want to know what the dilution factor is, you have to look at what's the volume of liquid in the pore spaces in contact with 0.1 kilogram of soil. And that's the pore water that's in equilibrium with PFAS in soil. And that's a very small number. So if we look at, let's say we have 0.1 kilogram of soil, that's 0.06 liters of soil. If we look at a 15% water saturation, we only have 0.004 liters of pore water in equilibrium with that soil sample. And now we're taking that soil and putting it in a 2-liter jug. So that's a dilution factor of 530 times, not 20. And then if you have 50% saturation, that's still a pretty significant dilution factor of about 160. So even where you've got 50% saturation, you've got a big dilution factor between SPLP tests and what would actually be measured in pore water, ignoring what's happening at the air-water interface. That's a second difference between water in the field in the vadosome and SPLP tests. But I just want to make the point, the dilution factor is not 20 times, that's a mass ratio. It's a much bigger number when you look at the liquid-to-liquid dilution factor. So what's interesting here is we looked at 1RI lysimeter, lysimeter 9, the SW, and we had available gravimetric moisture contents. If you're getting soil samples sent to a lab, the lab is measuring gravimetric moisture contents. You can actually use that to calculate the water saturation. There's an equation we go through, it's in one of our papers. Really helpful information if you're trying to evaluate what's happening for retardation factors, for example. So if you have soil samples analyzed in a lab, you have that moisture content data you can use to calculate water saturations. And then what we did is we plotted the ratio of the pore water concentration at this lysimeter divided by the SPLP leachate concentration. So a ratio of 400 to 500 for the short chain compounds that don't absorb to the air-water interface, that's really consistent with the liquid-to-liquid dilution factor we saw on the previous slide, 530. So this is because, okay, these compounds, they really aren't absorbing to the air-water interface. It's pure dilution that is causing the difference between SPLP and pore water, big dilution factor, big ratio between pore water concentrations, which are much higher than SPLP. Now, as you move from left to right, the chain length is increasing, and these compounds are more absorbing to the air-water interface. And this ratio is getting smaller because you've still got the same dilution, but now you've got more mass in pore water, sorry, not pore water, but you've got more PFAS mass absorbed to the air-water interface, and that reduces that ratio. So there's not one dilution factor you can use for all PFAS species. The ratio of these two concentrations is dependent on both the dilution factor. The dilution factor is the same for all species, but there's also the air-water interface absorption, which varies by species. And then we look at sulfonates, short chain PFB acid absorbs about the same amount as PFHXA, and it's got a similar ratio, pore water to SPLP results. And then we can see PFOA, the pore water is still higher than SPLP. And then PFAS, it's 5 times lower than SPLP. So if we were using SPLP to represent pore water concentrations, that would be 5 times higher than what we have measured in pore water for PFAS. But the key thing is I've seen some people multiply SPLP by some dilution factor, maybe 20 times, maybe something else. But the point is there's no one dilution factor we can use for all these PFAS species. If you wanted to adjust between pore water and SPLP, there's this equation that accounts for the partitioning that occurs. And that just shows the complexity between SPLP leachate concentrations, which are done under a saturated test, versus pore water, where you've got, especially for longer chain species, absorption to the air-water interface. And that results in lower pore water concentrations than what you'd think would be out there based on an SPLP. So let's look at, that was one lysimeter. So let's look at all the lysimeters from the RI. So now we're plotting radial diagrams again. One data series for SPLP. These are the saturated tests done in the lab based on the soil sample. And then the pore water concentrations from that second event in the orange data series. And you can see in the legend, the SPLP is about an order of magnitude higher than the pore water concentration for PFAS. And that's consistent with what we saw on the last slide. The air-water interface partitioning is greater than the dilution effects for PFAS. But every other compound, you can see the SPLP is less than the pore water, and the difference increases as you move from left to right, because you've got less and less influence from air-water absorption, and at PFBA, the difference is really caused by dilution. And the dilution factor is going to be dependent on the water saturation at each lysimeter. So just plotting these on the map, you can see the same thing. For PFAS, the SPLP tends to overestimate. Sometimes it's a little bit less, but it tends to be about half to an order of magnitude higher than PFAS, but then it's lower for most of the other species. So that's just something to be aware of, is that if you're looking at SPLP for KD tests, that might be representative, but I personally would use SPLP to approximate what the pore water concentrations are. We have to do a lot more sampling to try and estimate what that might be. And just to show you another difference that we see, which was kind of cool, was using the stacked bars to show us, we can see the carboxylates on the bottom. 6,2 FTS is gray, and the red is PFAS. The dark blue is PFOA. And when we plot the SPLP composition stack bars, these are all the lysimeters. These are based on leachate concentrations measured after the SPLP tests for each lysimeter. And you can see there's a lot of red, high PFAS in the SPLPs. There's a lot of dark blues. There's a lot of grays, the 6,2 FTS, the PFOA. So there's, and a lot of orange, the PFHXS. So a lot of the long chain species in the SPLP leachate. And that's pretty consistent with the soil concentrations. But it doesn't mean it's representative of pore water, because when we actually plot pore water, we see something very different, completely different composition. Now we're seeing maybe one with PFAS down here on the bottom, but most of these have no PFAS. 6,2 FTS is small to negligible. PFOA is quite a bit less in pore water, and we see a lot more of the short chain carboxylates, the greens. So what we're seeing is less long chains, which are absorbing to the air-water interface. That makes long chain pore water concentration smaller, and more of the short chains that don't absorb as well to the air-water interface. So that's a key difference between SPLP and pore water. This absorption to the air-water interface, where it's significant, means that the SPLP won't be representative of pore water composition. And just in case you're interested, like what is the ratio of mass absorbed to the air-water interface? That's the brown here. These are different water saturations on the bottom. Just looking at PFAS, we can see up to a water saturation of 75%, the majority of the PFAS mass is absorbed to the air-water interface. The yellow is what's actually absorbed to the organic carbon in soil, and the blue is what's actually dissolved in pore water, very small for PFAS until you get to the higher water saturations. And then the shortest chain compounds, you see obviously less absorption to the air-water interface, still some at lower water saturations, but it gets smaller as water saturation increases. So that's just something to help visually show you what kind of absorption you get in terms of proportion. And then PFAS leach, just a shout out to Bo Guo, he's developed this great model which represents that extra air-water interface partitioning. I did try that with one of the mass discharge cells at Ellsworth Air Force Base, got a very close result, just entering the soil concentrations, not entering pore water, and it actually predicted the mass discharge pretty well. Where I used the pore water to calculate mass discharge, the model matched that pretty well. I still think we have some work to kind of make sure the parameters we're using are correct, but it gives us an opportunity to something else we can factor in. So I've got about 5 minutes. There are a couple things I wanted to show. I'm going to go through this pretty quickly, but we're almost at the end, so I really appreciate your staying with us here. So I was giving a workshop at REMTech last October at REMTech Summit in Colorado, and I was wondering what data set can I use with low concentrations. New Jersey published this great data set from a statewide soil survey. So I basically used that data just to do some really simple forensics, just spent a couple hours developing some radial diagrams and stack bars just to see what the data showed. So I'll just show you the results. There are 157 superficial soil samples taken across the state, divided into these different counties. I'm going to show you radial diagrams and stack bars that represent the highest, the location of the highest PFAS concentrations in each county. So just using the heat matrix again, you can see very different from the one I showed earlier from an AFFF site. These are much lower concentrations. I've changed the intervals here, so we actually see more of a change across the different species. You can see PFUNA has the highest background, has the highest PFAS in soil. In the states, PFOA is the second highest. PFAS is high, but a fair bit less than the carboxylates. And then the other sulfonate species are all pretty low. So this just kind of tells you the magnitude of what you're seeing. No precursors, a little bit of HFPODA here, but fairly low, and low 6.2 FTS. And I just contoured this to get an idea of where do we have high total PFAS, where is it lower, so you can get an idea of the difference where things are high and low across the state. And you can see lowest concentrations are kind of in this area and in this area here. And stack bars for carboxylates. You can see just looking in this area, very different stack bars, a lot of species present, kind of at similar concentrations here, fewer species where a couple dominate. So I'd say those are two very different signatures. And you could kind of look through these and see where the differences are. But yeah, this stack bars, so helps you to look at kind of some forensics. And then radial diagrams, I'm not going to show you all the results, but I looked at arithmetic scale, log scale. I looked at, do I use different ranges for each axis or similar rate or same ranges for all axes? This is one location. And the thing with PFAS production is some processes will give more mass to the odd numbered PFAS or PFAS. In this case, PFNA is a C9. You can see C11 and C13 have higher concentrations than the other species here. And if you go to look at this on a map, you can see there's another location where the stack bar was different. This one actually has a spike at C10, C12, and C14. So that looks like maybe different manufacturing processes used between those two areas. So it's just the kind of thing you can see with radal diagrams. Where do you have some spikes that you don't see at most other places? Kind of tells you something you might want to go and take a look at. Where do you have non-detect symbols? There's some, but a fair number of detections across the state. And then just the sulfonates. Where do you have? It's mainly PFAS, as we saw earlier, with the maximum concentrations. A few locations with high PFDOS. Not sure what's driving that, but you can start to see where there might be some differences from location to location. Okay, and then just one final case study, really more for forensics. There's one groundwater well that's nested. There's pore water samples and surface water samples in a pond and in a surface water creek going downstream. This is the data, obviously hard to look at and come up with an opinion on what's happening. So one thing with radal diagrams, you can get magnitude signatures. We can see highest concentrations in the shallow, lowest at depth, a little bit higher, 34 to 35 feet. Might want to look up gradient to see what's happening there. So a very quick snapshot of how radal diagrams help with magnitudes. And then just looking at groundwater, this is the one groundwater well that's got a pretty similar signature to the pore water sample. Less sulfonates in the pore water, maybe from differential absorption to organic matter in the sediments, but not enough data to say for sure. But very different signatures from the other pore water samples further to the north. So it's showing that groundwater coming in this direction into the pond has a different signature in this part of the plume versus this part. And then if we add in the surface water, you can see directly down gradient of the pond, surface water is kind of a mix between the two signatures. And as you go downstream, it looks more and more like the groundwater up here. So that's just something that might indicate a connection between groundwater and surface water, but you need to look at that more closely. So just another example of how stack bars can be used for forensics and fingerprinting. So if anybody's interested in the Visual PFAS software, if you think it would help you with your work, we're happy to give you a free license and we'll offer you support with that. So just let us know. And on that note, I think I'll stop there and see if there are any questions. Thanks for all your attention. I appreciate that.
Wonderful. Thank you so much, Grant. Before I give people the option to unmute, I'm going to just quickly stop the recording here so we don't copy any of that.